Thanks very much. Thanks everyone for coming. So I'm here. We're both here today from Waterford, Ireland. Travelled over for DevConf to talk about P2CODE. So I'm Paul. We're on the EU Horizon research team. I'm an associate software engineer. And I'll let Clodagh introduce herself.
Yeah, so I'm Clodagh and I'm a software engineer on the same team as Paul.
Yeah, so P2CODE. So P2CODE stands for the Programming Platform for Intelligent Collaborative Deployments. Much easier just to say P2CODE. So the topics then for today's talk, so we'll be looking at the architecture, our contributions that we've been working on for the last 2 years. A lot of that is kind of aimed around the scheduler that was developed for the project, so we'll go into a little bit of that, and then how we extended the scheduler further out to the edge. Then look at the infrastructure that we had. We were in charge of deploying and rolling out across the 2 locations that we'll get into a bit later as well. The storage to support that, the telemetry that's behind that as well, and then how the platform is going to be utilized with 2 use case examples. So just a quick background then on the actual projects itself. So I'm not sure how many currently active Red Hat projects going on within the EU, the consortium group that's there, but our team itself works on 4 currently, and they're all kind of coming to the close in the next few months, so it's a very busy period across the 4 projects. The project itself, this one in particular, is just to create a trusted cloud-native programming platform catering for dynamic and distributed heterogeneous private edge infrastructures, as you can see on the slide. So essentially, we could deploy any app wherever needed across heterogeneous platform agnostic environments. So a quick look at the consortium on this project then. So it's made up of I think it's 17 in total partners across the project, ranging from universities or other big tech partners as well. Our main kind of people we'd actor in with quite a bit would be the MAID University in Milan, the University of West Scotland, the University of Patras in Greece, and UBTech, who would be the technical coordinator on the project. Yeah, so I'll just pass it over to Clodagh now about the key features.
So the main feature of the platform is the developer platform. So it's made using the Upstream Backstage project. So you have a load of CI/CD pipelines built into it and other tools to help you deploy your applications. A big advantage of the platform is that it has a unified orchestrator. So when you're dealing with 5G networks, cloud environments, and the edge, you have multiple different orchestrators. So it builds a unified one to help you manage all those territories in one solution. Next, then you have a unified network fabric. So you connect your Kubernetes and cloud native networking with any virtual network functions you have on your 5G networks as well. Then another main feature would be device verification. So in the platform, you have all your data center devices, and then you have your edge and far edge devices. So these are all verified before being onboarded into the platform, so you know that you're using trusted devices. So you look at things like the MAC address of the devices to make sure that they're all what you expect them to be. And then lastly, you have different users on the platform, so they've implemented role-based access to make sure that you're only accessing the systems that you need to. So you have kind of admin roles, then development and support roles. So there's a multi-layered architecture to the project. You have the infrastructure layer at the bottom. It's a multi-cloud setup. So we have a central hub, and then we have a load of smaller edge clouds that are connected up to the central hub, which is where all the main services are. The resource manager layer sits on top of that. That's built on top of something called OpenSlice. So that allows you to interact with your infrastructure. And then on top of that, again, we have the service layer. So that's where the user will be interacting mostly with the service layer. So they make their what's called requests for the different things that they need for the infrastructure. So kind of mentioned this as well before, but this is kind of the setup we have with the multiple clouds being connected all up into one. And that's very important for the schedule that I'll talk about in a minute. So each cloud had their own microservices there that allow it to talk up to the layer above it to kind of notify of what resources are available. So this is just more in detail of what's in the resource manager layer. So we have the scheduler, which we worked on quite a bit, storage, a resource manager. Then there's a series of controllers and drivers to mention all those different territories. So IoT, RAN, clouds, the network layer. Okay, so Paul.
Yeah, so our contribution then to the project, as we were saying, it's gone on for the last 2 years. So our main kind of focus is on the scheduler, looking at the resource manager, and then distributed storage across the test beds. So it's 2 test beds, one within the University of Patras in Greece and the other within the MAID Institute in Milan. They're both on different environments. So the Patras environment is on OpenStack, so we have OpenShift deployed on OpenStack there, and then the one in MAID, is vSphere, run on a vSphere instance. So we'll look a bit at the infrastructure a little bit later on, but essentially that's the core setup there. The telemetry then is a distributed Prometheus instance, federated Prometheus instances across the test beds to collect all the telemetry and push it back out to a Murmur instance, which we'll look a bit later at too. And then the rest of it then is just a spread awareness for the open source project's contribution. So we'll use OCM quite a bit, a lot, and poke back to that. So just pass back to Clodagh to talk to you about the scheduler then.
So the scheduler was like probably our core piece of work as part of this project. We were given some very vague requirements from the project as to what the scheduler should do. So they told us that it should handle multiple clusters, that we should also include special hardware that we available in those clusters, like consider there's GPUs, IoT devices. They wanted granularity to be able to target different nodes within a particular cluster or to target a particular cluster. And then they wanted to be platform agnostic, so they didn't want it to be too restricted. So if we had an OpenShift, K8s, Kubernetes vanilla platform, it should be able to handle all those different environments. So this is an overview of the scheduler we built. So as Paul mentioned, it's heavily reliant on OCM, the Open Cluster Manager, and that's the open source version of ACM, the Red Hat version. So the scheduler is an operator, Kubernetes operator that we wrote, and that's deployed on the central hub cluster. So it uses the placement and manifest work APIs that are part of OCM. So the placements, you're allowed to define certain requirements that you want your cluster to meet. So that API will help find the most suitable cluster. And then the manifest works helps you deploy your workloads to that particular cluster that you found. So also as part of this, then we create our own CRD to see up the yellow box. That is, so we call that the P2CODE scheduling manifest. So you can specify annotations there. They can be at the global or workload level. So at the global level, meaning that any deployments, manifests, like secrets, config max, anything like that, they'll all be treated with the same annotation. So if you want everything to go to a cluster in the EU region there, or everything to go to an OpenShift platform. So also as part of this then, the list of manifests, we have some intelligence in the background that allows the scheduler to bundle resources that it knows need to be deployed together. So it will analyze the deployment and look for any config max, secrets, PVCs, things like that need to all be bundled together. And then it's sent out to the different clusters. So this also uses cluster claims in the background. This is something that the cluster admin is responsible for setting up. So a cluster claim is basically a label in the OCM world that allows you to specify the capabilities of your cluster. So we requested all the cluster admins in the project use the prefix P2CODE.filter to use their annotations. So here an example of they can specify the region. So most of our clusters are in the EU, but the region could be, America or wherever. Then they can be more granular, saying a particular location like Athens or Italy. They have ones for distributions and in hardware. And this is a really flexible schema, so you can add anything else that you might need later on. So kind of mentioned that the P2CODE scheduling manifest then is where all your resources are listed. We also have, as well as the filter annotations, we have the target annotations. So you can target a particular cluster or a particular managed cluster set. So in OCM, a managed cluster set is a group of clusters that should be treated similarly. So you might have a cluster set for production or dev, like QA, that kind of stuff. So here's an example of a P2CODE schedule manifest. So as you can see, they can get quite long with all like the manifests indented in it. So then just very briefly, the benefits of this system. So we've basically built a wrapper around a lot of OCM artifacts. So it helps you work within OCM a lot faster. You don't have to worry about dealing with like the placement API, the manifest work API. It also takes a lot of the kind of like the overhead out of it. So if you give kind of like vague enough scheduling requirements, the scheduler knows how to interpret those and find the most optimal cluster. So I already mentioned about automatically bundling workloads that are to be sent to the same cluster together. So again, that kind of removes some of the burden from developers. And then another feature that we added recently was the scheduler can look at the deployments and see if some deployments need to like communicate with each other. And if they are scheduled to different clusters, we can set up scupper links to maintain the connectivity between them, even though they're on different clusters. So we also use a component that was delivered as part of another EU project, and we integrated in here to bring this all about. So another thing we did with the scheduler was we extended it to the edge. That was a requirement that was given to us by the project. So very briefly, I'll just mention what the Cloud Edge continuum is. So it's basically extending your cluster further and further out to the edge and out to like where the users are. So you have like your data center, and then you have like the near edge, far edge, and then like IoT devices and further away edge. So the solution that we built to deliver this is called Qubit. So it's just a play on words with Kubernetes and Bootsy. So Bootsy is a project that brings about bootable containers. So bootable container is sort of a specialized container that contains a kernel within it. So if you use certain build tools, you can convert that container image into a bootable artifact to boot a physical device or a virtual device. And you can use all like the normal cloud native tools that you would. So you can use like Docker, Podman, Scopio, all those kind of things. So we don't really have the time to go into like how this works in this talk here, but I have the link to the talk I gave in the Czech DevConf. It's another 35-minute talk, so these slides are uploaded as well, so you can get them afterwards. And then yeah, pass over to Paul for the storage stuff.
Yep, thanks, Clodagh. So the infrastructure on this platform, okay, so it was a bit of a nightmare for a good few months. Just for a little bit of backstory, we came onto these projects 6 months later, so they were already kind of a good bit ahead. So we were playing catch up from the start on this. It's just kind of how it worked out on the project. But essentially, we'd proposed a minimum of 2 clusters for each application area within the project. There's 4 application areas, so that'd be 1 Kubernetes cluster and 1 OpenShift cluster for each one. There is application areas were divided up between, it was 3 of them in Patras and then 1 in the maid facility, because it needed 5G capabilities for what they wanted to deploy there. So that's how that was looking. As I said previously, they had an OpenStack instance in the Patras, and then it was a vSphere instance in maid. So it was a bit of a learning curve. And again, they're all multi-tenancy environments. So to calculate the resources we were going to need, and then they were constantly changing back and forth, and how much they could give. Some of the other partners, because it's in universities as well, are sharing their infrastructure with projects going on within the universities as well. So something that was just easy, saying, hey, give me, I don't know, 500 gigs and 120 gigs of RAM and we should be fine, just turned into a war for months going back and forth with them. So we got there in the end. So resource management was a big kind of component going back and forth with our partners. As for the storage, then we were looking at having a Ceph backend for the OpenStack instance in Patras. So it's based on that. There's Cinder provisions volumes from Ceph, and it's managed within OpenStack. And then through that, we could call it into OpenShift and link it that way. But it wasn't really something novel enough for the project that it was just like, okay, we can provision storage that way. So we were looking at bundling OpenShift data foundations to to connect directly back to the Ceph backend, just by bypassing OpenStack completely. It gets a little confusing going OpenStack, OpenShift, OpenSlice. There's a lot of open utilities on the platform. So yeah, that's what we were looking at doing, and putting ODF to point back to Ceph directly and bundle that in. So we'll get into it a little bit later, but when there's Kubernetes as a service comes in through OpenSlice, it'll be bundled together. So it'll all just come up as one here's your new cluster, it's registered to the hub cluster, and then it's automatically having its storage connected to it. So that was that test bed. And then for the other test bed in Made, it was just a case of using NFS on AWS that they ended up migrating the whole kind of platform to. In the end, they moved away from vSphere. They had a lot of problems going on. It was a lot of push and pull back to it. So now they just have clusters on an AWS instance instead. And then for the K3S clusters that are run on the IoT devices, the decision was made to use NVMe local storage for them, or SD cards, whichever they had available at the time. So that's a current look at the proposed architecture we come up with. So you have your OCM hub at the top level, and then down underneath it, then you have your managed cluster sets. So within each cluster set, you have the one vanilla Kubernetes cluster and one OpenShift cluster. Then the ODF operator there to connect back to the Ceph backend, and then the three K3S clusters that we have in application area 1 on the left with the different sensors for each. So for telemetry then, it's a kind of similar workflow again. We basically have the top level, there's the ACM has an observability suite, which is just a federated Prometheus instance. So it can pull up all the data and the telemetry from each managed cluster within the cluster sets. That brings it up to the top level where we aggregate it all together and then push it back up to the top. The partner responsible for most of the telemetry work is Siemens. So we're kind of work hand in hand with them to get everything sent out to their Mirror instance that they use on AWS, and then they put it onto a dashboard where they report it and show all their telemetry data and metrics. For the K3S clusters, it's the same as connected to it, so we just run a smaller agent on it to pull the data up from them. And the same then proposed environment is there for the Made infrastructure. So it's a Prometheus, federated Prometheus instance at the top level to pull up the data from the clusters beneath it. So that's it there. As I was saying, so it's a similar enough kind of workflow to the infrastructure one that I had before, but that's that. Yeah. So the use cases. Then I'll just pass it back to Clodagh real quick.
So for all these EU projects, they always identify some like industries or use case areas to showcase the platform. So in this case, they chose logistics and transport, utilities inspection, smart factories, and public protection and disaster relief. So as part of these use cases, every edge site needs to be registered with the platform. So here's just an example of how this would be done. So imagine you have a factory somewhere with a 5G network installed. Then you register that with the core P2CODE platform, and then you register an infrastructure pool at the site. So if you have like your servers there, then you might have some factory workers, which might have some sensors, smart devices on them. These all then become registered into the infrastructure pool as well. Then once you have your applications written, you can deploy those out to any of the devices that are part of your infrastructure pool. So for example, here you might have some sort of like database running on your servers, and then some small, maybe like AI apps running on the smaller edge devices, which can then pick up some metrics from the workers, and they can use that to like enhance operations. So you can see that with some of the use cases here, which Paul will go through.
Yep, so just for the first use case then, you can see that there's a worker in a factory. So the factory itself would be registered to the platform, and they'd have their sensors and stuff placed around. But the worker itself would be wearing an exoskeleton, as you can see on the left, so they're just going about their day-to-day work. The exoskeleton itself would have a lot of sensors built in, so heart rate sensor, muscle sensors, so you can detect the level of fatigue. Or if the operator was going to be lifting particularly heavy loads, the user on the developer on the other end could just say, okay, we need a bit more power into this, and help them so they don't hurt themselves while they're at work. As you can see on the right, he's lifting a full pallet by himself, so it's doing quite a bit for him. And then here in the other use case then, so we have a kind of a search and rescue operation. So one of the use cases, the University of West Scotland has developed a facial identification application for their drones, so they can send it out for search and rescue. So as you can see, we'd have the two drones would be connected to the platform, and they'd be able to talk to each other. So you'd have the unmanned air vehicle, the drone there flying around. You could detect where the person is. They'd be able to send that telemetry data back to the drone operator on the ground in the unmanned ground vehicle, and they could go out for to rescue the person or send out assistance via emergency services. Yeah, so that's kind of the bulk of our contribution anyway and role into the project. So thanks very much for coming, and if there's any questions, we'll take them.
Your IoT devices. Wait. Do your IoT devices send telemetry to the same place as your cluster telemetry?
Yeah, so it all goes back up to the same Prometheus instance. It's just a federated Prometheus instance across. So there's a node agent that you can take from it to put on the IoT devices, because Prometheus itself would be way too much to be on those IoT devices. It'd be too heavy. Like, it's only, I think they're Raspberry Pi 5s. So it takes it up from that level and then pushes it up to the managed cluster set, kind of aggregates everything from there. But it can break it down further if it needs to say, okay, this is from this device.
Yeah, is there any GitHub repos that show how that's done?
There's not, because it is Siemens, our partner, who generally works on that. We're just there to kind of support the setup and deployment of everything. But once the project is completed, I would imagine everything will be out there. So there's a QR there for the main website for P2CODE itself, with additional resources on it. But it should be available kind of towards, I was saying, the project itself is wrapping up. It's finishing at the end of this year. So there'll be a lot more dissemination activities and papers coming out towards the end of the project itself.
Thank you.
No problem. Anybody else? Any other questions? Okay, great. Thanks very much. Thanks all for coming.